Wow, I actually did it. I'm in math. This is awesome. It's okay, nothing can hurt me here. Wait a second. Okay, today we're talking about identifying quadratic functions. And we got three ways we're going to talk about doing that. First is by looking at an equation. Second, by looking at a table of values. And third, by looking at its graph. Now, if we're looking at its equation, every quadratic can be written in this magical, wonderful thing called standard form of a quadratic function. Anyways, standard form of a quadratic function, y equals ax squared plus bx plus c. A, b, and c are some numbers, can be anything except a cannot equal 0. That's important because this guy, x squared, is the most important part of a quadratic function. If it has an x squared, it's quadratic. If it doesn't, it's not going to be quadratic. Also, the x squared has to be the largest variable exponent. So if there's an x cubed or an x to the 4th power in the problem, it's not going to be quadratic. So it has to have an x squared, and that has to be the biggest variable exponent there is. This sounds simple enough. There's an x squared, it's a quadratic. So if you were looking at all of these, could you tell which ones are quadratic? If you said that one, that one, that one, nice. Those are all quadratic. That one's not, because it has an x cubed in it. Can't have an x cubed. That one is it, because it's missing its x squared. Has to be an x squared in order to be quadratic. So good job? Maybe? I don't know. Anyways, so let's try the example. Y equals x squared. Is it quadratic? If it is, can you identify A, B, and C? Yeah, it's quadratic. A is 1. There's nothing multiplying the x squared, so we can imagine there's a 1 there. B and C are both 0. There's no x term, there's no number term, so B is 0, C is 0. That's fine as long as A isn't 0, and it's not. It's 1. So that is quadratic. Good job, maybe. So on to the practice problems. Practice problem number 1. Is that quadratic? If so, write it in standard form and identify A, B, and C. Now, I don't remember what I said earlier, and I refuse to rewind, but I should have said a quadratic function is anything that can be written in standard form. So on practice number 1, we could make this in a standard form if I move that 3x squared over, like this. Anything you do to one side, you have to do to the other. There it is. So it is in standard form, where A is -3, B is 0, and C is 2. Yeah. Practice problem number 2. Is that one quadratic? No. No x squared term, not quadratic. Simple as that. Okay, so identifying a quadratic by its equation, simple enough. Can it be written in standard form of a quadratic function? Stop it! Yeah. And if it can, great. If it can't, it's not. Second way to look at them is by looking at its table of values. So if we look here at our example, we got all of our inputs, x, and all of our outputs, y. So let's It's a little complicated, but we have to look at our change in x. And if we have a constant change in x, it should result in a constant second change in y. Now what's a second change in y? So if we look at our example here, x increases by 2 each time, plus 2, plus 2, plus 2. And if we look at our y, to get from 8 to 2, it went down 6. And from 2 to 0, it went down 2. Then from 0 to 2, it went up 2. From 2 to 8, it went up 6. So that's the first change in y. But for quadratics, we want to look at the second change in y. So we go from negative 6 to negative 2. That's up 4. From negative 2 to positive 2, up another 4. And then from positive 2 to positive 6, up another 4. So if we look at our change in x, it was constant, plus 2 every time. And if we look at our change in y, the second change was constant, plus 4 every time. So this is a quadratic function. Here's an example of one that would not be a quadratic function. It had a constant change in x, but the constant second change in y, there was not a constant second change in y, so it's not a quadratic function. If on a worksheet I asked you to explain whether one was or one was not a quadratic function, we could say something like, yes, because a constant change in x resulted in a constant second change in y, or no, because a constant change in x did not result in a constant second change in y, if it came up on a worksheet that you might have at some point in your life. Way number 3, to identify something as a quadratic function. We can look at its graph. Now the graph of all quadratics will always be parabolas. Insert cool parabola video. Parabolas can face up or down. They're kind of U-shaped. Some are fatter and some are narrower than others. We'll get more into that later. But the graph will always be parabolic if it's a quadratic function. So if we're looking at a picture of a graph, if it's a parabola, it's quadratic. If we have to make our own graph, luckily we know how to do that. If we go to the back page, we got an example there. Y equals 2x squared. We know it's quadratic because it's written in standard form. So after I graph it, I should get something that looks like a parabola. In order to graph functions for now, we're just going to pick inputs and get outputs, creating ordered pairs. We plot the ordered pairs, and hopefully our graph looks kind of U-shaped when we're done. So we can pick any x's we want. Considering my graph only goes from negative 4 to positive 4, I should pick x's that are between negative 4 and positive 4. We want to pick negatives and positives so that we get the whole picture of what the graph's doing. Let's just pick negative 2, negative 1, 0, 1, 2. That works. So we plug these inputs into our function, get out outputs, thus generating ordered pairs, which we can plot on our graph, and hopefully it makes a parabola in the end. So if I plug a negative 2 into this function, I get 2 times negative 2 squared. PEMDAS, so exponents first. Negative 2 squared is positive 4. 4 times 2 is 8. So when I plug in a negative 2, I get out a positive 8. On the next one, when I plug in a negative 1, I get negative 1 squared is positive 1. 2 times 1 is 2. So I plug in a negative 1, I get out a 2. When I plug in a 0, 0 squared is 0. 2 times 0 is 0. I get out a 0. So I get 1 at the origin, 0, comma 0. When I plug in a 1, 1 squared is 1. 2 times 1 is 2. I get out a 2. When I plug in a positive 2, 2 squared is 4. 4 times 2 is 8. I get out an 8. So I plot all these ordered pairs on my graph. Hopefully that worked. And connect them with a nice smooth curve. And look, it makes a parabola, which is what I wanted. On practice number 2, you take a moment to try and do that yourself. I guess you can just push the pause button. Yeah, that makes sense. Unpause. Did it look like this? Bloop, bloop, bloop. Hopefully, yeah. If not, this is what you should have done. So if we look at the two graphs from our examples, you can notice right off the bat that they're different in one pretty big way. One's facing up, one's facing down. That's because of our a. A on the first one was positive 2, and on the second one was negative 2. When the function's written in standard form, if a is a positive number greater than 0, then it's going to face upward, open up. If it's a negative number, a number less than 0, it'll open downward, face down. So when it's written in standard form, we can tell which way it opens by looking at our a. So which way would the two problems on our examples open? I'll give you a second to think about that. On example A, my quadratic function is already written in standard form, and a equals 4, which is greater than 0, so that one's going to open upward. On B, it's a little bit trickier. It's not in standard form. Standard form is y equals ax squared plus bx plus c, and this one has 2x squared plus y equals. It needs to just be y equals, so I need to get rid of that 2x squared. To do that, I want to move it over to the right side where it belongs, so I subtract 2x squared from both sides of my equation, and lo and behold, now my function is y equals negative 2x squared plus 5. Negative 2 is less than 0, so it's going to open downward. So be sure it's written in standard form before you tell if your parabola opens up or down. Last thing, we're going to talk about some of the properties of a graph of a quadratic function. They have what are called vertices, vertex, plural, vertice, which is either a high point or a low point on a parabola. So if it opens upward, the lowest point on the parabola is called the vertex. If it opens downward, the highest point on the parabola is called the vertex. All functions also have what are called domain and range. Hopefully we remember. Domain is all input values, x values. In a quadratic function, unless I tell you what the domain is, you can always assume that the domain is all real numbers, because you can plug anything you want into a quadratic function and get something out. The range is a little different because there's only certain things we can get out. Since a parabola has a high point and a low point, that means our y values are constrained. So if a graph opens up and has a minimum value, I can't get any y values that are lower than whatever that minimum is. So our range will be everything greater than the minimum. Or if it opens downward, our range will be everything less than the maximum, if that makes any sense. So on the example, which will help show it better, A, which is over here, first question it wants us to answer is where's the vertex? It's right there at 3, negative 2. Then it asks for the minimum. This is a parabola that opens up, so it has a minimum value. The minimum is always equal to the y-coordinate of the vertex, since that is as low as it will go. So on this one, our minimum is negative 2. Next, it asks for the domain. Domain, unless I tell you otherwise, is always going to be all real numbers, because it has arrows there and there, meaning it goes forever to the left and to the right on the x-axis. So my domain is all real numbers. And lastly, the range. The range is y is greater than or equal to negative 2. The reason being that's our minimum value, and range is all possible y values. So since that's a minimum, I'm not going to get any y values below that line, but I can get y values above that line. And since there are arrows there and it goes forever in the upward direction, it's anything greater than negative 2. So whenever we have a minimum value, my range will always be y is greater than or equal to that minimum. If I have a maximum, then it'll be y is less than or equal to whatever that maximum value is. So you try and do B, and then we'll go over the answers. So these are the answers for B. Our vertex is at 1, 2. Our maximum is at 2. Our domain, again, all real numbers. And our range is y is less than or equal to 2. Any questions? Well, too bad. All right, so we got 3 ways. I don't like that. Nope. By the equation, by a graph, or by a table of values. That makes sense to do it. If it's written in an... What are we doing? Anyways, standard form of a quadratic equation. y equals ax squared plus y. It's pretty important because in order to be quadratic, it's all about that guy. If there's an x squared, x squared is the most important part of a quadratic function. Blah, 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 everybody say. On A, I don't like that. We're starting over. Vertex, which is either a high point or a low point in a parabola, depending on whether it opens up or down. They also have a bunch of other attributes, which I can't remember right now. Oh yeah. Since parabolas have a minimum and maximum value, and our y point, it can't get any lower than that, but I can get out any ones higher than that. Any ones? Ones what? What's happening? No. So if we look at example A, for example, example